The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you all are getting up early now, because I see you all are sending me good morning messages, and I think it is not just to please me, like you send a message and then again you go to bed, because getting up early is very important. The whole body actually rejuvenates in the morning. When you become active, the brain is very active in the morning. You could do good things, energetic things, keep yourself refreshed so that you have your breakfast, lunch, everything on time. The moment you get up early, the whole day schedule actually gets disturbed. Your body metabolism gets affected and then your brain actually becomes inactive. We don't realize this now and it becomes too late when we realize it. So I want my children to get up early, and I know you all are sending me messages, but I believe you are doing it not to please me, for yourself, right? So we were in the 4th chapter actually, and today we are going to start with a new theory. We started learning about Lewis concept and how it was helping us, and now we are going to start with valence shell electron pair repulsion theory. Now in this theory, we have certain postulates. Now why did this theory arise? It's just because Lewis concept was not able to tell the geometry of the molecule, nor about the electron pairs perfectly, because there were some drawbacks, incomplete octet, or you can say expanded octet, some of the limitations that were there in the Lewis concept. So now here we are going to start about VSEPR theory, which is called as valence shell electron pair repulsion theory. Valence shell means, I know you all would have studied about the electrons present in the outermost shell, which is called as a valence shell, which takes part in the chemical reaction. So those valence shell, there is an electron pair repulsion. That is, any electron there will be a repulsion, because we know like charges, they repel each other. So this is the theory which we are going to see now, and how this helps in finding out the geometry of the molecule also we will be looking at. First, let me explain you the postulates that are involved in VSEPR theory. When I say the postulates, the first and foremost is shape of molecule is being assigned, or shape of the molecule completely depends on number of valence shell electron pairs around the central atom. We have a central atom, we have the atoms which are getting bonded to the central atom. So the shape of that particular molecule depends completely on the number of electron pairs. Now those can be bonded or it can be non-bonded electron pairs also. Also the valence shell electron pairs, they repel each other, and also with the electron cloud. See, I have an atom and I have some of the atoms Y. So the electrons which are present here are negatively charged. Now those electrons can also repel with the electron cloud, that is the space where there are again electrons which are negatively charged. The third postulate, they try to have a space orientation with the electron pair so that they minimize repulsion. They try to have a proper geometry in space so that there is a minimum repulsion and maximum distance between the electrons, so as to reduce the repulsion between the two like charges. Now the valence shell will be considered as a sphere where the electron pair is being completely localized. They get distributed into the sphere at the maximum distance. They try to occupy the maximum distance so that the sphere will be completely filled with the electron pair at maximum distance to avoid to avoid the repulsion. Any multiple bond that is formed between the two atoms will be considered as a single electron pair, because we know one bond represents one electron pair. So, multiple bond will be representing a single electron pair, and if you have 2-3 electron pair, that will be regarded as a super pair, that is super pair, where there are more than one electron pair present between the two atoms. Any molecule which can have 2-3 resonance structure definitely will have a VSEPR theory applicable to it. So, a molecule that has 2-3 resonance structure which is possible for that particular molecule can definitely go with VSEPR theory. Now, VSEPR theory is completely dependent on this. What is this? Lone pair repulsion being greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. What is the reason behind this? When I say bond pair, that is between any two atoms, and when I say lone pair, that is present around the central atom. So, this lone pair which is around the central atom has got maximum repulsion around it, and there are maximum distance also which is possible. So, what happens? That repulsion will be greater, but there is no restriction of the distance or area. But when I say bond pair, it is only between any two atoms. That is, I have two atoms, the distance between these two is the bond pair. So, the repulsion will also be only between these two. So, that shows their repulsion will be least, then comes lone pair bond pair, then the greatest will be the lone pair repulsion. Now, this VSEPR theory is based on two important concepts. One is central atom without the lone pair and central atom with the lone pair. So, we will be seeing the different geometry where the central atom is having lone pair and central atom having no lone pair. So, with this, let us begin the different geometry of AB2, AB3, AB4, AB5 and AB6. I hope you have your textbook with you, because individually examples are so nicely given in the textbook with different lone pair bond pair structures, and also I will be posting a video for your clear understanding. Children, now you can take your textbook with page number 110, where you can see there are 4 columns given. The first one is number of electron pairs, then second one is arrangement of electron pairs, then you have molecular geometry, and then you have some examples given there. If you see number of electron pairs 2, the example is here AB2, where this is my A, this is my B, chlorine are my B and this is my A, 2 electron pair, this is 1 electron pair, this is 1 electron pair. So, this forms a linear structure with 180 degree. Next one is AB3, where you have this is boron my A and 3 fluorine atoms as my B. Bond angle is 120 degree and having 3 bond pairs, and this showing a trigonal planar structure. Next one is CH4 AB4, carbon acts as A and hydrogen acts as B. There are 4 bond pairs with 109.5 degrees. 109.5 degrees and forming a tetrahedral structure. Next one is AB5, trigonal bipyramidal structure, here with an angle of 120 degree and this with an angle of 90 degree. There are 5 bond pairs forming a trigonal bipyramidal structure. And the last one is forming an octahedral structure, SF6, or I can say AB6, forming an octahedral structure with 6 bond pairs, and you have 90 degree formed at certain angles. So, these are the central atom with no lone pair of electrons. We have only bond pairs between 2 atoms. This is the first table given to you in the textbook. Very important. 2 or 1 example is given for each structure. Learn the structure with example. Just need to by heart it from the table. The next table in page 111 shows the central atom with lone pair and also bond pair. If you see, the second column shows the bonding pair and the third column shows the lone pair, and the arrangement are also given, and you can see around A, the central atom, how many lone pairs are given. The molecule type is given as AB2E, where E represents the lone pair. If there are only one lone pair, we will write E. If there are two lone pair, E2. If there are three lone pair, E3. But you have structures only with two lone pair around the central atom. So the shape is also given to you. Examples are also given to you. They will not ask to explain it, but they may ask you to draw the diagram with an example. Right. Now we will get back into valence bond theory. Let us now see about the valence bond theory. In valence bond theory, if you see, valence bond, that is the electrons which are present in the valence shell will be bonded. In this, if you see, these are completely dependent on the atomic orbitals, that is the orbitals which are in the atoms and the electronic configuration of the elements which decides what type of geometry can be possible. Overlap of the atomic orbitals, that is the orbitals get overlap with each other, and also the hybridization of the atomic orbitals. Now let us consider an example. What is exactly this valence bond theory means? If you consider two hydrogen atoms, I have an hydrogen atom, one more hydrogen atom. Now if they are far away from each other, there is nothing happening between them. But once they come closer to each other, there are some sort of attractive force or the repulsive force that is existing between the two hydrogen atoms. Now this is my hydrogen atom A having a nucleus A with an electron A. My hydrogen atom B having a nucleus B and an electron B. Now what are the two types of forces that are possible? You have the attractive force possible between the nucleus of the first hydrogen with the electron of the first hydrogen, because nucleus being positively charged try to attract the electron towards itself. So there is an attractive force within the molecule. Similarly, the nucleus of the atom B with the electron of its B atom. And what is the next attractive force? The nucleus of the first hydrogen can attract the electron of the second hydrogen, and the nucleus of the second hydrogen can attract the electron of the first hydrogen. So these are the attractive forces that are possible. Now do they have repulsive force? Yes, definitely they possess repulsive force also. How? The nucleus of hydrogen atom 1 repel the nucleus of the hydrogen atom 2, and the electron of the first hydrogen atom will repel the electron of the second hydrogen atom. See, this is my hydrogen atom A, this is my hydrogen atom B, this is EA, electron of the first hydrogen atom, this is EB, electron of the second hydrogen atom. Now when they attract, what happens? This is plus attracting the negative charge plus attracting negative charge. So they tend to come closer to each other. Now what are the repulsion possible? These two are negative, so they go away from each other. These two are positive, also they tend to go away from each other. Now the new attractive force, which is the new attractive force? The first nucleus of the hydrogen atom attract the electron of the second hydrogen atom. Similarly here, the nucleus of the second hydrogen atom tend to attract the electron of the first hydrogen atom. They are more than the new repulsive force. So the energy will be released where there is a new bond formed between two hydrogen atom. That energy released will be called as the bond enthalpy. So that is more than the repulsive force and tends to form the bond formation with an attractive force between the new hydrogen nucleus and the electron pair of another hydrogen atom. Such an enthalpy we call it as a bond enthalpy. So this is with the valence bond theory, where the atomic orbitals tend to attract the electrons of the other atom. Now let us study about the orbital overlap concept. How does this orbitals tend to overlap with each other? We are going to study about the orbital overlap concept. What do you mean by orbital overlap? We have been learning that we have subshells, subshells has got orbitals, and those orbitals take part in the bonding formation. Partial merging of atomic orbitals. What is merging? Merging means joining. the partial merging of the atomic orbitals is called as orbital overlap, or we say overlapping of the orbitals. Greater is the overlap, stronger will be the bond that is formed. So, the overlap, if it is getting greater and greater, the bond formed will be very, very strong. And that will have some directional property, because a covalent bond is formed by the orbital overlap of the atomic orbitals. So, that shows certain directions. What do you mean by direction? In which side does the electron pair gets attracted to a greater extent? So, that is done with a small example. If you take hydrogen, two hydrogen atoms combine to form a hydrogen molecule with 1s orbital overlap. Each hydrogen has got a 1s orbital. So, these 1s orbital tend to overlap with each other, forming a new bond. So, that new bond will be formed and that will have certain directional property. So, this valence bond theory helps us to give the shape also of the direction property of these bond that is formed as a result of this theory. Now, these orbitals forming the bond, they can have the same sign and also they have the same orientation in space. Such a orbital overlap, we call it as a positive overlap. You have negative overlap if the overlap is not with the same sign. You have zero overlap also, which is given in your textbook, but we will focus on most of the positive overlap. If you take an example of methane, carbon having an electronic configuration of 1s2, so this can be written as noble gas He, with 2s2, 2p1 at ground state, but at excited state one of the electron from the s subshell jumps to the p. So, it becomes 2px1, 2py1 and 2pz1. So, this carbon has got 4 bonds with hydrogen, where the 3 CH bonds tend to have a 90-degree, but the 4th bond that is formed with the S overlap with another of the hydrogen may not be forming a 90-degree, so the bond angle remains ascertained. So, that bond angle was found to be tetrahedral, that is why 109.5 degrees we say. So, CH4 forming a tetrahedral structure. This is mainly focused on the types of overlapping that is formed between the two atoms. So, and that decides the nature of bond also, whether it is sigma bond or it is pi bond. So, let us learn about sigma and pi bond in detail, then we will get into the new theory, that is hybridization. Now, we are going to study about the types of overlapping orbitals and also the nature of the bond. First is the sigma bond. Sigma bond is formed by the head-on overlap, or I will say axial overlap along the internuclear axis. So, you have 3 types here: SS overlap, SP overlap and PP overlap, where S orbital of one atom combines with the S orbital of another atom, forming a new bond. So, this is called as a sigma bond, which is on a head-on overlap, or I will say axial overlap. When S orbital of one atom combines with the P orbital of another atom, you get again a new bond that is formed. When P and P of two atoms, when they combine, you get again a sigma bond that is formed. Now, what is pi bond? Pi bond is formed by the sidewise overlap of the atomic orbitals, where you can see the P bond, P orbital of one bond combines with the P orbital of another bond, forming a pi bond. So, this is called as a sidewise overlap, and where when multiple bonds are formed, you get a sigma bond, and on the top and bottom are made up of pi bonds. So, these are the pi clouds which are formed between the two atoms, and when you compare the strength of the two atoms with the two bonds, the sigma bond are actually more stronger because they have a head-on overlap, axial overlap, which makes them more stronger, as the extent of overlap is also getting stronger. But when you compare pi, that is a little bit weaker bond as compared to that of the sigma bond because of the sidewise overlap. That is why we say when we have this multiple bond, only the pi bonds are broken and the sigma bond stay in the same place. So, that is with orbital overlap concept. The next will be focusing on hybridization. In hybridization, if you see in page number 116, please mark it important, children. The definition is given under hybridization: the process of intermixing of the orbitals of slightly different energy. So, when I say a p orbital subshell having 3 orbitals, the energy between these 3 orbitals are not that different. not that huge. It has a slightly different energy. They intermix with each other so as to distribute their energy, and they result in the formation of new atomic orbitals, which we call it as a hybrid orbitals. And let us see the salient features one by one. First one is the number of hybrid orbitals is equal to number of atomic orbitals that get hybridized. Example, if 3 atomic orbitals are getting combined, I get 3 set of hybrid orbitals formed. If 4 atomic orbitals are combined, I get 4 hybrid orbitals that are formed as a result of this hybridization. The hybridized orbitals are always equivalent in energy and shape. Before hybridization, they will be slightly different in their energy level, but after hybridization, they have the same shape and the same energy. Third one, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. When I take a pure atomic orbitals, they don't have a stable bond formation, that is, they are unstable. Anytime their bond can be broken. But once they get hybridized, that set of hybrid orbitals, they have a very stable bond as compared to that of the atomic orbitals. The last one, these hybrid orbitals are directed in space in a preferred direction to have minimum repulsion between the electron pair and to get a stable arrangement. Once the hybridization process is over, these hybrid orbitals, they tend to get themselves arranged in space in such a way that they form a stable arrangement or a configuration so that to have a minimum electron repulsion. Therefore, this indicates the geometry of the molecule. Why they need to arrange themselves in space is just to get a geometry. Now, what are the important conditions? Those were the postulates. Let us study the conditions for hybridization to occur. The first and foremost condition, the orbitals present in the valence shell of the atom are hybridized. The valence shell has got some of the orbitals. They are the one who are supposed to get hybridized. The orbitals undergoing hybridization should have equal energy, almost equal, not a very big difference in their energy level. Say I have 3 atomic orbitals which are about to get hybridized. All the 3 should possess an energy which are little bit almost equal in them. Promotion of electron is not essential condition prior to hybridization. What is promotion of electron? An electron in the ground state getting itself promoted or getting itself upgraded to the next energy level is not an important condition for hybridization to occur. It is not necessary that only half-filled orbitals can take part in the hybridization. Even filled orbitals or filled electrons in the valence shell can also take part. Orbitals which are half filled is not necessary for hybridization. Even fully filled orbitals but which are present in the valence shell can take part in the hybridization. So, let us learn one by one about hybridization in detail. Let us now learn about hybridization in detail. So, first we are going to see sp hybridization, then we will see sp2 and then sp3. So, these are the 3 common types of hybridization which will be coming across. The first one, if you see sp hybridization, you have one s orbital hybridizing with one p orbital to form 2 sp orbitals, because I told you number of atomic orbitals that hybridize will be equal to the number of hybridized orbitals that are formed. So, here one s and one p, 2 atomic orbitals are combining to form 2 sp orbitals. Since it is an sp hybridization, there is a 50% of s character and 50% of p character, and it forms a linear geometry, or I can also say it forms a diagonal hybridization. If I take the example beryllium chloride, beryllium atomic number is 4. So, you have 1s2, 2s2 in its ground state, but when it gets excited, one of the electron from the s orbital jumps to the vacant 2p orbital. So, you have 2 unpaired electrons. So, 1 electron from 2s and 1 electron from 2p, they get hybridized to form 2 sp or orbitals, which will be combining or forming a bond with a chlorine atom which needs 1 electron to become octet. So this formation BeCl2, beryllium chloride, has an sp hybridization with a linear geometry forming 180 degrees. Now we shall move into sp2 hybridization. In sp2 hybridization, from the name it is clear that you have 1 s and 2 p orbitals which combine to form 3 sp2 hybridized orbitals. It forms a trigonal planar structure with a bond angle of 120 degrees. So let us take an example of boron trichloride. Boron is a central atom having atomic number 5. So that is 1s2, 2s2 and 2p1, where 2 electrons are there in the s orbital, from which 1 electron jumps into the vacant p orbital, forming 2px1 and 2py1. So what happens here? There are 3 unpaired electrons in each of the atomic orbital which will combine together to form 3 sp2 hybridized orbitals. So this is the structure where you have a trigonal planar structure with a bond angle of 120 degrees. Now we shall learn about sp3 hybridization and also some more examples to understand it better. sp3 hybridization, where we have 1 s orbital combining with 3 p orbitals to form 4 sp3 hybridized orbitals. In this, since it is sp3, the out of 100% we will say 25% of s character and 75% of p character, and it forms a tetrahedral shape with 109.5 degrees. Because what happens here, if you take the example methane, carbon with 1s2, 2s2, 2p, it is 2. So what happens here? Here we have 4 bonds. So from 2p, 2 electrons are there, and here 1 more electron jumps to 2p. So that become 4 unpaired electrons which will be hybridizing to form 4 sp3 hybridized orbital. Now when you take ammonia and water, these are exceptionals which are showing sp3 hybridization with a lone pair present around the central atom. Nitrogen has got 1 lone pair which is present. So with other 3 electrons, P3, it forms a pyramidal shape with hydrogen of 1s. So ammonia forms a pyramidal structure with a bond angle reduced to 107 degrees. Water, when you take, it has 2 lone pair of electrons. So with that, the shape becomes V shape or angular in geometry, or the bond angle getting reduced to 104.5 degrees. So these are the examples which are already given in the textbook. We will definitely get the focus areas. Which we are going to see now is molecular orbital theory. In this, there are 2 atomic orbitals. That is, in hybridization we were seeing the atomic orbitals, they combine to form the hybridized atomic orbitals, but here there will be atomic orbitals which will be combining together to form the molecular orbitals. So we get molecular orbitals here as a result of combination of atomic orbitals with bonding and anti-bonding orbitals. Now what are these bonding and anti-bonding orbitals? Bonding molecular orbital will have lower energy and greater stability. Lower the energy of the bonding, greater will be the stability of the molecule. And the electron distribution, that is the probability of finding the electrons around the group of nucleus, because this is a molecular orbital, definitely there will be so many nucleus found. So the electron probability of finding the nucleus around this group of nuclei will be given by the molecular orbital, and definitely it follows the filling of Avber's rule, Pauli's exclusion principle and Hund's rule of maximum multiplicity. Now what do you mean by molecular orbital theory? See, there was Schrodinger wave equation which was first designed to find out the distribution of the wave function, that is the amplitude. But what happened later, it was not able to give a correct crystal idea of where the electron probability is there, or how this electron comes out of the orbital to get hybridized or to get mixed. But then it was started that molecular orbital theory followed a method of linear combination of atomic orbitals. That is, the atomic orbitals will be combined in a linear fashion to get the molecular orbital, which was given by psi, the wave function molecular orbital, a combination of addition and subtraction of the wave functions of the two individual atoms which combine to form a molecule. So it forms two type of orbitals. One is a bonding, the other one is anti-bonding. In bonding, it's an addition product, and in anti-bonding, it's a subtraction or after substitution. The difference of two wave function is the anti-bonding, and the addition of two wave function is the bonding. So this we define as bonding and anti-bonding. Now we will be having certain examples in your textbook also, like which I will be putting a video, because children, once you are here, I will be showing a video to understand how the electron move and how do they form the molecular orbital concept. Okay. Now you need some conditions, which are the combining atomic orbitals must have the same energy, just like our hybridization, and the combining atomic orbitals must have same symmetry, that is the orientation must also be the same. The combining atomic orbitals must overlap to the maximum extent so that they gain the maximum stability. Now types of molecular orbitals, you have different types of, that is sigma with bonding and anti-bonding. So children, I hope you would have understood the topic for today. With this, we will wind up the class. We have some more topics which will be taken in the next class along with a new chapter. I will be definitely posting the videos, because these are the things which you should be seeing the videos and understanding. Normally when you come here, we do that. So definitely the related videos, I will be posting it. Do understand the video, and if you have any doubt, when you come here, we can clarify it. Okay children, thank you so much. Take care. Bye.